So I'm driving across the country, and it's God knows where we are, and we're really tired. We drive right until nightfall. We pull over to the side of the road. It's a beautiful moon-filled, starry night. We just throw out our sleeping bags. We sleep right down on the ground, and I notice it's crunchy. I wake up in the morning, everywhere it's white. We're in the Utah Salt Flats, and the entire surface, as far as the eye could see, is nothing but this stuff. Sodium chloride. Nothing but ionic bonds. Let's take a look at ionic bonds, talk about what they're like, how come, and there you go. This is Screencast 7.4. Well, one neat thing about ionic bonds is what happens when you throw them in water. Let's be sure we know what an ionic bond, or salt, is. It is a substance which has a metal connected to a nonmetal. There's a staircase right around there. These are all metals. These are all nonmetals. That's how you identify them. They dissociate when you throw them in water. Now, normally a bond is a really hard thing to break, but with salts, they break just by throwing them in water. There's ample evidence, particularly, conductivity evidence, that says, sodium chloride will form the sodium cation and the chloride anion in water. Evaporated, it comes back together. Funky, right? Another thing about salts, besides the fact that that AQ means aqueous, put a little aqueous, that means dissolved there, is that these bonds right here are very, very strong. After all, sodium chloride melts at like 2200 Celsius. You can put it in your oven, set it to broil, and nothing happens to it. But on the other hand, they're very brittle, and this has to do with the fact that the electrostatic attraction is really strong, plus to minus everywhere. Looks to me like is yellow plus and blue is minus. In any event, this is supposed to represent a salt. The reason they're brittle is because one little frame shift can cause a huge linear crack. Imagine somehow pushing this row over 1. Then instead of all plus minus plus minus plus minus, it all becomes plus plus minus minus plus plus minus minus. And you get huge repulsion and crack, and that's responsible for those 3,000-foot cracks you see on El Capitan in California, for example. Okay, so let's talk about naming them. Suppose you got the sodium cation and the chlorine anion. Naming it's easy. We just call it sodium chloride. The charges, sodium is +1, there it is, +1, chlorine, -1, a match made in heaven, a nice ionic bond. To write that formula, you just switch the charges and you write NaCl, which is, unnecessary here, but we're going to need to do it here. Mg and F. Magnesium fluoride, right? Notice how you always take that anion and add the little IDE. You're used to doing that, right? Stannous fluoride in toothpaste, for example. The charges, however, in this case, are +2 for magnesium. See that? It wants to lose 2 electrons. 2 valence electrons, wants to dump them. Fluorine only wants to gain 1. So if these things just hook together, we have a charged species. That's unstable. But if we just have a second fluorine anion, then we're good to go. Because it's a total of -2 there and a total of +2 there. And there you go. So it must be MgF2. That's the long, slow way to figure out how to come up with the formula. The quick way is just to switch the charges. If you just take that 2 and put it down there, and that 1 and put it down there, you'll instantly get the molecular formula. The only time you'll get it wrong is when you have to subsequently reduce. So if it's like Mg4F2, you reduce it down to Mg2F1. People drop the 1. Right? See how we drop the 1? Nice. Okay, this is Screencast 7.4.